Welcome to part 9 of the lecture on designing organic syntheses. Let us start with a simple looking example, which become much more complicated as we further go into the retrosynthetic analysis of the structure. So, let us look for strategic bonds, and clearly here this double bond of the alpha-beta unsaturated carbonyl compound is a strategic bond, since these bonds are easily synthesized by aldol condensation. Therefore, you of course can directly transform that in our retrosynthetic analysis to this acyclic structure. And now we have quite a lot of relationships between carbonyl groups, a 1,4 relationship, another 1,4 relationship, a 1,3 relationship, a 1,6 relationship. So, we are forced to have a closer look in which one is the favorable to set up in the next step. Well, so let's add some numbers. R1 at this position here, or let's see, here the R2, there the R3, this the R4, and as I said, we already also have a 1,6 relationship, and R5 should be also a way for going on in our retrosynthetic analysis. R1. So, it's clear here we have a 1,3 relationship. This is somewhat favorable because we would have the natural reactivity as donator reactivity here. So, and at the carbonyl group, we have as natural reactivity the acceptor reactivity. So, just adding a synthon, well, that has acceptor reactivity here. We need a leaving group. And the most simple leaving group in that case would be, of course, just an ethoxy group. So, why not planning to apply this with simply ester, and well, here we have the donator reactivity should be the enolate. Of course, we should check, do we have a high selectivity in this case for deprotonating right here? Well, okay, thermodynamically, the deprotonation here is preferred since the enolate is rather highly substituted. So that means thermodynamically it might be preferred here, but the C bond formation at that center won't be thermodynamically favored. That means the next step isn't, since we would get to a quaternary center. So it could happen that in equilibrium it's deprotonated here, it's deprotonated there, sometimes also deprotonated there. Then it's protonated again. The most species which are enolates are those that have the enolate here, but they are less reactive with the electrophile than the others. Okay? So that means we would get a selectivity problem. Therefore, we should think about an alternative. Let's say we call that R1 prime, where we say, well, okay, we have the introduction of the same functional group in mind, but we turn the sequence around, just say, well, we don't disconnect first here, but we just disconnect here. Let us assume that we try to form this CC bond while that ring is still present, or already present in our synthesis. So, well, that means again, donator functionality here, and, well, the same electrophile applied. Now the deprotonation here has an additional advantage, since this is then an ion is part of a linearly conjugated and therefore stabilized anion. So, stabilization is even better. Well, you get also deprotonation here in conjugation to that double bond. However, in this case, we have a cross-conjugation, and cross-conjugation is inferior in terms of the stabilization of our system. Okay? So, it might be better to apply that structure as an ion rather than that one. In addition, this would avoid in brackets the problem that under the influence of a base, you also have a selectivity problem for that final aldol condensation process. Since you could deprotonate here and make the CC bond formation from here to there, resulting in this structure. But what does the system hinder in the fact that it could be deprotonated here and the CC bond formation takes place from here to there? So we have, for sure, in that case, the competing reaction forming this structure. Well, under the usual reaction conditions, there might be an equilibrium between those two. Okay, you can say, well, let's isolate that one and then put that into the conditions of the equilibrium. Well, maybe it works, but for that equilibrium you have to add, normally, I'm thinking about that right now, sodium hydroxide, and heating it up. This will cause a problem because the ester functionalities will be hydrolyzed then. So these are all considerations one has to go through while making the plans for synthesizing a molecule like that, of course. So, okay. Now, this seems to be rather reasonable. Okay? Let's check the next one, R2. So we need donator reactivity here and acceptor reactivity to introduce that structure. Well, it's an acylation, and the leaving group here, X, might be a chloride, so acetyl chloride, or it could be an acetate itself. That means we could try to apply the anhydride, or maybe just an ester will have sufficient reactivity in terms of ester condensation. So let's write down, take a base for that reaction. Well, and we will notice we have a problem, since certainly it won't be selectively deprotonated alpha to the ester functionality, simply because alpha to the ketone is more acidic. We won't get the acylation done at that position. Won't work. So let's go on with R3. With R3 we have clearly 1,4 relationships, from that carbonyl to this one or to that one. This is the double activated center. Therefore, here we would choose to have the donator reactivity, and then we need for that carbon the acceptor reactivity. And therefore, R2 will lead to these two synthons, donator reactivity here, acceptor reactivity there. Let's translate that into synthetic equivalence. Here the leaving group, the bromide, and there let's put on the anion with an sodium counter cation, which is of course coordinated to the oxygen of the enolate. Well, okay. Doesn't look that bad, since if we have the neutral species and add a base, then for sure it would be deprotonated here, since that is doubly activated, as I already said. Okay. Seems to be okay. Nevertheless, we should still consider also in that case R3 prime having that ring system still present. Well, okay, it's still double activated at this position. However, maybe you already notice a problem here for that. In this case, we should draw mesomeric structures which will tell us something about the reactivity of that system. So, if we have that ring system, we will deprotonate here, and overall we will have delta minus nucleophilic centers, 3 nucleophilic centers. This one, that one, and also the oxide. We can guess where preferentially the reaction with the electrophile will take place, and I'm pretty sure it won't react very likely at this position, since again we get a tertiary, a quaternary center. That means steric hindrance. It will preferentially react for a CC bond formation at this position. Right, so we have selectivity problem. I would guess it won't go into the direction we wanted, and therefore we should add a question mark there, since imagine that under basic reaction conditions you have that system, you can't be sure that this reaction here is fast enough. Maybe in that reaction mixture already that condensation reaction could occur. So that means also here you could get a similar selectivity problem as you have here. So we have to add serious question marks about the reliability of this synthetic plan. R4 we should therefore have a look at. Next. So, again, what is R4? It's this one. So, setting up a 1,5 relationship from that carbonyl to that, as well as from that carbonyl to that, 1, 2, 3, 4, 5. And those 1,5 relationships are favorable. So it's R4 okay, donator reactivity, no problem. It will be for sure deprotonated here. And in addition, setting up that structure, no problem. Acetic acid, acetoacetic acid ester, deprotonated, and let that react with the bromoacetic acid ester. No problem to get that one selectively. And this is treated the presence of a base with MVK, methyl vinyl ketone. Yes, it will work. However, presumably you will already get under the basic reaction conditions that cyclization should remind you of the Robinson annihilation process, but in this case it's not the Robinson annihilation process, since in an annihilation process you have a ring system and add another ring to it, okay? But it is essentially the same sequence of Michael addition reaction plus aldol condensation, cyclizing aldol condensation. So it should work, but with a selectivity problem there, that you have two ways where how the final aldol condensation can take place. Aber it looks okay. Finally, R5. A 1,6 relationship between carbonyl groups. You should always think about oxidizing a cyclohexene moiety. So that means retrosynthetic analysis 5 leads us to this structure, and I think you will all agree that this is a significant simplification, since this cyclohexane we could set up then by a Diels-Alder reaction. With this diene, a very well-known diene, this is isoprene. Therefore, this looks so tremendously simple, of all those ideas and plans, one for sure would try this one first, I think. So, after I was talking that much, I would like to suggest that you think about the retrosynthetic analysis for this product. And already one hint, there is a problem of stereo selectivity connected to this structure. It is achiral, but one has to think about synthesizing this diastereo selectively, that, well, you have a cis-fused system. This 7-membered ring is large enough that you also could have a transfused situation. So please think about how to synthesize such a structure. How should I start that retrosynthetic analysis? And well, if you don't find the solution, it's not that easy, but then you should find the problems which are connected to the synthesis of that structure. So let's discuss some of the suggestions I've noticed. Well, this came to your mind, of course, and means you were thinking about something like that, acceptor reactivity, donator reactivity. So then, how should one get acceptor reactivity here? Well, you need leaving groups. And hoping for an SN2 type reaction, then those two leaving groups should be on the same side of the ring. Well, okay. And there was also already an idea how you get those on the same side of the ring. First, a cis dihydroxylation. Secondly, tosylation, for instance. There are some problems connected with this idea. It's not that easy to get hands on that compound, since the double bond easily isomerizes in under acidic as well as basic conditions, but it is conjugated. Okay. The other, even more serious problem is that there is no good idea for a synthetic equivalent of the structure. So it's not easy to well, to define something useful there that has a chance to work. Moreover, if we have with some kind of nucleophile a donator reactivity here, that means at the same time we have basic reaction conditions. And under basic reaction conditions, elimination reactions should occur. Well, then there was a similar idea connected with that. Well, maybe one could get to the synthons. Well, okay. Let's hope that we somehow get hands on this cuprate. And on the other hand, this one. Not easy to get to that. On the other hand, it's maybe even more difficult to get to that one, since this structure is known to have anti-aromatic character. I think we talked about that before. In fact, structures like that have been applied as synthetic equivalents for this one, since after the first cuprate addition, then an elimination could take place here, and later on, normally as a two-step process, performing two cuprate additions, conjugate addition reactions. And while in addition, why having these groups connected? Well, because of the idea hoping for the connection will make sure that both go into that molecules, or both connections will be formed, well, from the same side. Oh well, doesn't look that promising. I think you agree. Yeah? Well, there was another idea introducing these hydrogens from the same side simply by a heterogeneous hydrogenation reaction. Yes, why not? Again, also in this case, you have a problem that this double bond likes to isomerize into the conjugation with a carbonyl group. Well, okay. Alternative. Let us add a functional group here at this position. This looks, of course, more complicated than that, but now we can take a Dieckmann cyclization into our retrosynthetic. Can consider it within our retrosynthetic analysis. So you know Diekmann cyclization simply is an ester condensation which is performed intramolecularly. So now we have a 1,6 relationship between those two carbonyls. Let's draw that cyclohexene structure again. Here we have an acetal. So acetone plus this bis hydroxymethyl compound. So, and these hydroxymethyl groups you might get, or usually would get, by reduction of these carbons at the oxidation state of a carboxylic acid. So reduction with lithium aluminum hydride. So, and this is of course the product of a Diels-Alder reaction of butadiene with maleinic anhydride. This easily then explains the diastereoselectivity which we need for the synthesis of that. Okay, not that you get now the impression that every synthesis problem can be solved with a Diels-Alder reaction, but a lot of them can. Let's have a look at another example which I think offers a nice exercise. Please think about how to synthesize this structure. When analyzing this target, it's certainly not a bad idea to try the first disconnection here, since electronization will certainly occur if you have intermediary, either an acid here or an ester. And here we still have that side chain with the ester functionality. Some of you then had the idea that we have a 1,6 relationship, 1, 2, 3, 4, 5, 6, and we could make use of that by this retrosynthetic step which indeed would be a nice simplification. However, we have a problem that this dimethoxybenzene may be lithiated here or maybe electron rich enough, should be connected with this reagent, the problem into conjugation. Well, this has the big question mark. Therefore, let's try the disconnection here. Donator reactivity here, acceptor reactivity there. So, we are in need of some kind of organometallic species. Well, there are several possibilities. What we could try is, for instance, metallate with bromoacetic acid ester. Lithiation, well, lithium is not the metal of choice in this case because this organolithium species will react with the next ester functionality, of course. The classical way to achieve that is with the metal, well, an organo-zinc compound. This is then called the Reformatsky reaction. In recent times, however, also Grignard reagents were found to be acceptable, applicable in that case, but under certain reaction conditions, not with the direct magnesium insertion here, of course, but the reaction conditions developed by Paul Knochel. We discussed that within the lecture of about stoichiometric organometallics. Well, what you also could do is deprotonating, for instance, with LDA and trapping with TMS chloride. That you have an ester enolate as a nucleophile. Okay, and then activating with a Lewis acid, you could also achieve the CC bond formation of this CC bond. So what we should clarify now is how do we get to this structure? Okay, here we would disconnect in our retrosynthetic analysis. I think it's not necessary that I write that down. This is obviously a Friedel-Crafts acylation applying, well, best would be presumably applying succinic anhydride as the electrophile. Then you have a carboxylic acid at the end there. Maybe you should form an ester then for achieving this reaction. Next exercise. please try a retrosynthetic analysis of this target. So the first step in the retrosynthetic analysis of this target is, of course, simple. The other steps then are somewhat tricky, as we will notice. We would disconnect here, accept a reactivity there, donator reactivity there is natural reactivity, so straightforward would be this retrosynthetic transformation. So, because with sodium ethanolate in ethanol and heating it up a bit, we should get a rather good yield of this one. Now we have again a 1,6 connectivity between the carbonyl groups. We should check the idea using an ozonolysis of a double bond or an oxidation of a double bond in setting up those two carbonyls. And you will find out that you would be in need of this olefin. Unfortunately, this olefin is forbidden under Brett's rules. In small bicyclic systems, bridgehead olefins are not allowed, well, they are not, simply are not possible. So, therefore, we would choose to disconnect this bond accept the reactivity here, since it is the natural reactivity of that alpha beta unsaturated ketone. But we are in need of this as donator reactivity, and maybe let us directly translate that into synthetic equivalent, a cuprate. However, the problem is, how do we get that cuprate? It's not easy to set that up. Why? Well, metallation of a halide in that position is a problem, since instead of metallating here, you will normally observe an elimination reaction here. Because metallation is basic and it will then react with the next molecule of that kind. It's difficult to set up something like that. There are some synthetic equivalents known, because this is known as a problem and chemists have tried to solve the problem. But no easy answers to this question. There's an alternative idea. Why not, again, using this, the second step, a homologation. That means we have to elongate that side chain by just one CH2 group, and such reactions that are capable of that are known. So, let's see. Retrosynthetic analysis with this idea in mind could be this. Let's change here to a cyano group. We have still the same oxidation state here as there in the ester functionality. Then disconnect here. Leaving group and a cyanide as the nucleophile. That leaving group might derive from an alcohol, which then could derive by reduction from an ester. However, reducing that ester to the alcohol is only feasible if we have that carbonyl group protected. So, this is the retrosynthetic analysis, and it has been done as a real lab synthesis. First, a malonate under basic conditions was applied for introducing the side chain. You have to hydrolyze then the ester moieties, acidify and heat it up, then it will decarboxylate. One acid functionality will decarboxylate, and later on, also under acidic conditions in ethanol, corresponding ester was synthesized. And this product was isolated in 80% yield. This is really a good yield for this multi-step transformation. Introducing the protecting group. Worked out with 88% yield, then reducing with lithium aluminum hydride, produced that alcohol with 85% yield, all steps with rather good yield. Then transforming it to a leaving group, with tosyl chloride and pyridine, (74% yield for this step). Secondly, reaction nucleophilic substitution with potassium cyanide, 81% yield. Now we are here with this structure. First, HCl, water, heating it up, somewhat rather drastic reaction conditions for the hydrolyzation of that cyano group. At the same time, of course, that carbonyl group is restored again, is deprotected, and under these conditions, already some aldol processes might take place, and this explains why after the final esterification it was reported that they had reached this intermediate product, but over these two steps, just 52% yield. With sodium ethanolate in ethanol, and then, of course, acidifying under moderate reaction conditions, since under the basic reaction conditions, this is of course deprotonated here because of the double activated CH group here, methane group, and you have to acidify it, and then you have that product, 70% yield. So if you calculate the overall yield of this sequence is just about 13%. So we should think about a maybe somewhat more clever alternative. One alternative with that elongation. One could start here with that ester or the intermediate carboxylic acid, trying, for instance, an Arndt-Eistert reaction. This is such an elongation. You need a chloride. Let this react with diazomethane. Secondly, treat that then, the intermediate, under silver catalysis, then you will get to the elongated carboxylic acid, well, with one CH2 group more here introduced. However, the problem, I think, is already that step, as I told you, the hydrolyzation of that cyano group. And so also the Arndt-Eistert reaction will not affect a much higher yield, much higher overall yield. So maybe a somewhat more clever idea is this one. Again, this is our target. Maybe you could achieve having these, well, saturated, mainly saturated moiety by starting from an unsaturated system simply with catalytic hydrogenation. Therefore, one should think about just hydrogenate this molecule, for instance, with hydrogen and Rene nickel. Maybe you can get to this product without losing the OH group. This might be a problem, but it is that an intermediate is sensitive and could lose, well, could condensate just losing water. And well, from here to there, no problem, oxidation there. However, this, of course, derives from this aldehyde. Unfortunately, the aldehyde in the meta position, you can synthesize that, you can buy that, and you might look in SciFinder how to synthesize a molecule like that. So I think enough for today.